Welcome to the second week of this course Newtonian Mechanics with Examples. In the previous week, we covered a little bit of mathematical preliminaries on scalars, vectors and tensors. So, this week we are going to start with the physics topics proper. So, we shall start with reviewing the basic Newton's law of motion. So, before going into the subjects, I feel that this is a good point to sort of discuss a little bit about the philosophy and the learning objectives of this course. So, first thing is that you can expect that there will be lot of examples as the title suggests, and these examples will be taken mostly from our everyday day to day life. So, I mean the point is that if you want to sort of learn to mechanics well, you need to build a good physical intuition about the real life experiences. So, that being said, I want to make a couple of remarks. First is that I assume that all of you have already seen mechanics at the high school level. So, I will deliberately try to avoid those examples which are very common in high school textbooks, such as for example, pulley. So, the emphasis will be on the real life part, where so the textbook examples that you have seen are somewhat kind of ideal. So, they ignore a lot of crucial aspect. So, we will include all those crucial aspect, and that will give us a correct physical intuition. I will tell more about the real life examples in the next slide. Before that, the second sort of focus of this course will be of course, there will be lot of problem solving, and in this case my goal is to sort of to develop a kind of general strategy or a general way of thinking about how to approach any mechanics problem. So, the point is that usually the mechanics is considered to be a difficult subject, and students often do not know how to approach a problem when the problem is unknown. So, if they have seen the problem before, they know how to solve it based on some formulas that you may have kind of remembered, but the goal is that without remembering any formula, how can we think about the problem. The second point is that, so this course is intended to be for first year students of various engineering disciplines as well as physics students and other science streams, chemistry, maths, biology, etc. So, here I sort of say a few remarks about what I feel is the somewhat difference about approaching mechanics from engineering point of view and from physics point of view. So, engineering is about control. So, you want to design some machine which you can control to sort of get a output in a controlled way, whereas the emphasis of physics is on how to find the basic principles or basic equations to analyze the machine. For example, the task of an engineer could be to design a machine, and once you make a design, a blueprint, you go ahead and build the machine in the real life, whereas the task of a physicist could be to identify the working principle that explains how the machine works, also to identify the conditions when the design will break down. So, the problems that we discuss, so we will try to make a balance between these two aspects, so that the whatever engineers who typically sort of focus on this part of the problem in their various core subject areas will have some idea about these points which are not usually covered. On the other hand, when the physics students and other science students, they you should expect that so you will get to know somewhat realistic aspects, real life examples. So the textbooks tend to cover more very schematic idealistic version of different mechanisms and machines. So, we will try to see somewhat more real life oriented application, so that you sort of have a better idea about real life. So, given these learning objectives, so here is the outline for this week 2. So, first we will sort of introduce a kind of general way of strategy for solving mechanics problems, which we call the system interaction picture for problem solving. Then, so first we will discuss what is the systems. We will take several examples, and in particular we shall introduce two very common mechanical model. One is point mass and one is rigid body. So, these will be kind of repetitively used in various examples, so that we shall summary the essential points about them. After that, we will talk about interactions. So, we will review our basic concepts about forces, taking examples of common forces in daily life, and then we will talk about little bit about the fundamental forces and modern physics point of view about forces. And we will talk about an important aspect of the effect of force on motion. Then we shall go and about reviewing of Newton's laws of motion. Now, I am sure that all of you have already seen Newton's laws of motion. So, my point of view in this course will be that I will assume that you know Newton's laws of motion. So, I will sort of tell you how to use or how to apply these Newton's laws to analyze the mechanics problem, to solve mechanics problem. So, we will keep this particular picture in mind when we review the Newton's laws. Then we shall use this Newton's laws to classify the different types of problems. So, you see that in mechanics there can be infinite number of problems, and obviously, if you want to develop your skill in solving mechanics problem, the only way to do that is to sort of take a problem, struggle with it and solve it. But obviously, you have only finite amount of time, you cannot solve infinite number of problems. So, a smart way is to sort of know what are the different types of problems, and then sort of know how to approach each type of the problem. So, this is what we shall do by starting from just by using Newton's laws, and then we will focus on an important technique for analysis, which is called the free body diagram. So, how to draw free body diagram, we will quickly review it, and we shall see that in order to draw free body diagram correctly, you need to keep in mind about 3 different points about the forces. So, how to think about any mechanics problem. So, this is our picture. So, we will divide the analysis into 3 different pieces. So, the first piece is system. So, you identify the system. The second piece is interaction, identify the forces, and then you do the modeling, which means to apply the basic physics principles. So, you do not have to memorize formula, instead you just remember the basic physics principles, and then you write down equations, and once you have the equations, then and you know what are the known quantities given in the problem and what are the unknown quantities, you try to solve those equations. So, this is the scheme. So, let us see what is meant by this system interaction picture in more detail. So, consider this example of this book on a table. So, for example, that imagine this is a table and I put a book on the table and we solve. So, this is our very simple mechanics problem. So, maybe the table the book is at rest on the table. So, then the question could be that what is the condition under which the book will be at rest on the table. So, what do we mean by system? System is the part that we want to focus on, we want to know the properties or the part whose motion we are interested to study. For example, in this problem the system could be our book. Usually this is specified clearly in the problem. Sometimes it is not, and then we have to sort of use our experience or some thinking to identify the system, but this is usually the easy part. Then everything else that is outside the book is the surrounding. So, what we are doing here in this picture is that this is our entire universe, and this entire, so this green blocks represents the entire universe, and what we are doing is that we are dividing the entire universe into two pieces. The first piece is this system. So, in this example this is this book, that is our system, and then everything else that is outside the book is that part of the universe is called the surrounding. Now, why do we break this into these two parts? Because the surrounding and system interact with each other. So, what could be the surrounding in this problem? So, in this problem the surrounding is obviously, you can think of the first thing is the, let us say this is the table. So, the table, the book is in contact with the table. So, obviously table form is an important part of the surrounding. What is maybe less obvious is that in this problem the earth is also part of the surrounding. Why? Because earth is also interacting with the book. So, the earth is pulling the book is feeling a force of gravity due to the earth, which is the weight of the book. So, earth is also part of the surrounding. So, now we sort of describe, like mention about these two very simple mechanical models, which we will be using in various forms throughout this course. The first model is a point particle or a point mass. So, an example could be this famous problem of the motion of earth. So, this is the earth and this is the sun. So, the earth is moving around the sun. So, this is a very famous and one of the earliest mechanics problem. This is called the Kepler problem. So, the problem is to what is the path or the orbit that the earth takes to move around the sun. Now, as you know, or you can easily imagine that in this problem we represent both the earth and the sun as a point. So, we ignore that earth has some size and some particular structure, we just assume them is a point. Similarly, we think about the sun also as a point. So, this is an extreme simplification of a object, usually a solid object, that you ignore the size and internal structure of this object. Now, the point is that you can do that depending on the problem at hand. I mean, the same object can be thought of as a point in one situation, but may not be thought of as a point in another situation. So, we will see different examples of that kind, so here, so this is just an example of a point particle. So, anything can be represented by a point particle. Now, what are the types of motion that a point particle can have? So, how can it move? So, there are three basic types of motion you can easily think of. One is that it can move in a straight line. So, that means that it is moving without changing its velocity. So, these arrows here represents the possible direction of velocity of the particle. So, obviously, this particle, suppose this is a particle, it can move in a straight line in one direction. Now, if it moves on a plane, then let us say in the plane of this book, the book cover, then it can move in any direction along this cover of on the plane of the book cover, and this direction and this direction can be resolved into two independent parts. So, this is what we have seen in the previous week in the context of vector. So, the velocity is a vector. So, it can be resolved into two independent components. So, two direction. Similarly, in 3 dimension, let us say in this room, if a point particle is moving, so it is in a straight line, it has 3 independent components. This is what is shown here by these 3 directions of arrows. These are like Cartesian, think of them as Cartesian axis. The second way it can move is, it can move in a circle, the circle about some external point which is the center of the circle, and you can maybe imagine as an axis which is passing through the slides perpendicular to the slides. So, it is moving around, that is the axis of rotation. So, it is moving in a circle. So, what is the difference between moving in a straight line and moving in a circle? So, in the straight line, when it moves in a straight line, the direction of the velocity is constant, whereas when the direction of the velocity is in the tangent, in the direction of the tangent. So, it is continuously changing at every point. This is about the direction. What about the magnitude? So, the simplest very special case, or the simplest case maybe perhaps, is when the magnitude of the velocity is not changing. So, that is possible when it moves along a straight line. It is also possible when it moves along a circle. So, the magnitude is not changing, but the direction is continuously changing. So, the velocity has two aspect, the magnitude and the direction. So, the velocity of the particle has a magnitude and a direction given by the unit vector along the direction of velocity, and you can you see that these are kind of independent aspect of velocity. So, you can change magnitude keeping velocity direction fixed, you can change direction keeping magnitude fixed, and then you can think of that there could be a more complex complicated path that the particle can move, which is some sort of a kind of, you can perhaps can be thought of as a combination of a straight line movement and a movement in a circle. So, this is a example which can be analyzed as kind of a combination of a movement along the straight line and then along a circle. So, here I ask a question and I will leave it for you to think further. So, the question is that can a true point mass, like really a point who does not have any size and any structure, exist in real life? So, the next example of systems that we will be interested in this course are objects which have some, which cover some areas, extended objects. So, their structure and size cannot be ignored, and here are a few examples. So, they can be of different types. For example, this is a compact object, then these objects can be not so compact, such as this tree in this photo. Then we can have some example in which there are multiply connected objects. So, there are different objects such as which are connected by various joints and pivots, such as the example of human body. For example, if we think of our arm, so this is, we can think of this arm as sort of having a connected piece. Let us say this is one piece, this is another piece, this is perhaps another piece, and they are connected at joints. So, the movement of our arm is not a single object, but at least three different connected pieces joined by some pivots. This is an interesting example. So, this is a sand art. So, this is a sand Taj Mahal. So, this is an example of a solid object which is made of small grains of sands. So, I put it to sort of show that there is a lot of variety about solid objects, and the rigid does not always mean that hard or strong. So, why do I so I mentioned this word rigid. So, this is the second very simple model of a the mechanical model that we shall use. So, this is for an extended object, this is for an extended object. So, a rigid body is an extended object in which the distance between any 2 points are always fixed. So, if I take let us say sphere and take any 2 points, let us say this is the center and from center any points, or this point to this point any 2 points, the distance is always fixed. So, if you think about it, it means that the body is always moves as a whole. So, for example, if I look at this object, so this is an kind of a solid object. So, this is you can think of as a rigid object. So, if it moves, the everything moves, not a all the points in this paperweight moves together. So, the whole body kind of moves as a single unit. Consequence of that is that if one knows the position of a single point in the body, one knows the position of the whole body. We shall see in the later part of the course that one often takes a special point inside the body about a special point which is called the center of mass. So, this is the second extremely simplified mechanical model. Why do I call it extremely simplified model? Because in this case, when we represent let us say a solid object, we sort of keeping the information about the size and structure, but we are not allowing any deformation of the object. So, because deformation means you are trying to change the distance between 2 points inside the object, which is not allowed by definition of a rigid body. So, this is why this is a ideal case. Any and ideal model, very simple model, the moment you include deformation, the analysis of the problem becomes more complicated. So, again I leave this question for you to think about. So, can a true rigid body exist? Can you think of any example of a truly rigid body in real life? So, here are some examples of various types of motion of a rigid body. So, like before in the case of point mass, it can move along a straight line such as this train moves on the straight railway track. It can also move along a curve. For example, you know that railway track can also be curved at certain places. Apart from that, it can show rotational motion. So, these rotational motions we shall see of can be divided into different categories. So, this is a example of a mechanism inside a clock. So, you can maybe call it as a clock pendulum. So, this is an example of a fixed axis rotation. So, the axis is fixed, this is the pivot point and this is rotating, and this wheel is the pivot point for this wheel, and this is rotating about this pivot point. Then we can have some very complicated motion of a rigid body. So, you can imagine that possible motion can be more complicated compared to a single point particle. So, here is an example. This is called the crankshaft mechanism, sliding shaft crank mechanism. So, this is a combination of a translation and rotation. So, this kind of mechanism is very common in various such as vehicles such as car, etc. The one motion that is not possible for a point particle, because it does not have any it does not have any size, is that a point particle cannot rotate about its own axis, because it does not have any extension size. This is possible for the case of rigid body. So, for example, if you look at this toy, it has a it is a toy with a wheel. So, this wheel can rotate about an axis which is represented by this axle of the wheel. So, this rod which is the axle of the wheel. So, this wheel can rotate about itself. So, a rigid body can rotate about an axis passing through itself. So, that means that when a rigid body moves, in general its motion is always a combination of translation and rotation. So, this aspect we will discuss in more detail in the later part of the course. After that, this introduction to so now we have some example and ideas about systems, and I have seen 2 mechanical ideal cases of systems that we will consider. Let us discuss review about the common forces in everyday life. So, here is a table in which the second column represents some common forces, the common names of the forces. So, first is the third column and fourth column gives you the magnitude and direction of the forces. The first column will come in the next slide, and at the moment the last column is put some comment which you may ignore at the moment. So, the first point to mention is that the one first very important force is the weight, the gravitational attraction by earth, that we everyone on living on earth always feels this force. So, our everyday experience, our physical intuition about the day to day life or our surrounding is heavily biased by this force. We always feel this force, and as you know that the magnitude is given by the mass of an object times the strength of the gravitational field at the location of the object given by small g, which and small g you can calculate using the Newton's formula for universal gravitation, and this force is directed towards the center of the earth, which is on the surface of earth. It means that it is vertically downward along the the radius towards the center. The second very important force that heavily bias our physical intuition and everyday experience is friction. So, here is a common example of friction. So, we as a human being, we are immersed in an atmosphere of a fluid, the air. So, when we move, and sometimes we are also immersed in the water, we swim or going somewhere through boat or something. So, we feel this friction by air and the water. These are called drag force. So, we will come to that more detail in later part of this course. So, friction is the another very important common forces. Then but if you think about mechanical force, usually we think about a pushing force or pulling force or tension force, something like which in general called the contact force. And so, the prototype example will be perhaps a block on a plane problem. So, this is a block which is on an inclined plane with an angle theta, and then there is a force of interaction between the block and the plane, and this in general has two. So, this is you know that it has two components in general. So, the component normal to the plane and the component tangential to the plane. So, this represents the friction, and so other one is called the normal component of force. So, we will come back to this force in more detail later. So, we will take examples of that. So, but this is like one force that sort of is a kind of mechanical force, another very common example. And then finally, we have a model which is called spring force. So, this is again a very useful force both for engineering application. So, spring is extremely useful, not only because of the mechanical springs that we can use to build various mechanical part of a mechanism, but also it has an exact analogy in electrical circuit. So, in terms of the components of capacitors and resistors and so on. So, this is a very useful for practical application point of view. In physics also it is a very important force, because this is the most one of the most simple force that we can often in a complicated situation we sort of make progress if we assume that the interaction forces are like a spring force, which is given by this simple formula F equal to minus kx, where x is the extension of the spring. Now, I must mention that from modern 21st century physics point of view, so all these different forces, there are only kind of 4 different fundamental interactions. So, the strong nuclear force, the weak nuclear force, the electromagnetic force and the gravity. Now, the strong and weak forces are exist only within a nucleus. So, outside nucleus, anything that is atomic size onwards. So, all the forces are either electric force, electromagnetic force or the gravity. So, gravity is so in our list basically the fundamental origin for, so for all these forces which are except the weight of an object are basically coming from the electromagnetic interactions due to the charges, electrical charges and electrical currents at the. So, this is a very fundamental picture. We shall not go into very detail about this picture in this course, but the engineering students should keep this in mind, this fundamental picture. Now, I point out one interesting fact that the electromagnetic force is usually extremely strong compared to the gravitational force. For example, here I show the electromagnetic force comparison of calculate the electromagnetic force between two electrons at rest. So, at certain distance r, and what is the value of the electromagnetic force, the Coulomb force is obviously very small, but the value of the gravitational force between two electrons at the same distance is extremely small compared to the electromagnetic force. So, that is why in day to day situations we only gravitational force we consider or we need to consider is when one of the object is the earth, that is the gravitation due to earth, or you need to have an mass of the scale of the size of earth to really consider the electromagnetic interaction. Now, the another point that I will quickly mention, so that before going to the Newton's law, is that what are the effects of forces. So, we shall see in the next lecture that the forces causes acceleration. So, this is the Newton's law. So, basically it means that if you apply, for example, if I take this book and if I apply some forces, I push this book, it will start to move. Now, there are two types of motion possible. One is translation, which means it is start moving in a straight line, and the other is rotation. So, this is sometimes will be little bit counterintuitive, but the effect of force. So, force can also cause a object to rotate, and so this is a very simple way to understand this, that for example, if I take this book in this position and sort of take it as a hinge. So, imagine this is like a door, and then if I apply some force, then you can see that it will start to rotate about this backbone of the book as a about this backbone of the book. The point is that to analyze the rotational aspect of the force, you know, in the previous so force is a vector. So, it has a magnitude and direction, but this in addition to magnitude and direction, we need to know the line of action of the force, which is also equally necessary to analyze this effect of rotation. So, that is why we need this quantity called torque or moment of the force. So, I just quickly define the what is torque. So, the torque is, as you know, is defined by this relation that. So, for example, you consider this gear gear wheel. So, there is a force applied on the edge of the wheel in a certain direction as represented by this red arrow, then and this is O is the pivot point about which the wheel is rotating. So, then the point of application, so R represents the position vector of the point of application of the wheel, and then the torque is defined by this cross product between the R and the force F. And if you apply the formula for cross product, you will turns out that the magnitude of the torque is given by the magnitude of the force times the distance between the line of action. So, this is called a line of action. So, if you extend the direction of the force on both sides, this gives you the line of action. So, the line of action of the force and the distance, by distance I mean the perpendicular distance. So, if you drop a perpendicular from O, pivot point O to the line of action, then this represents d. So, that gives you the so that d multiplied by force. So, the point is that the rotational the rotational effect depends not only on F, but also on this distance d. Now, there are two remark. First is that if you move this, so this is the line of action. If you move this force without changing its magnitude and direction along this line of action, it does not change the torque. First thing, this is called the principle of transmissibility. Second is that if the line of action passes through the pivot point, then the moment of the force, that is the torque, is 0. So, why? Because if line of action passes through the same force, if it passes through this point through O, then the distance from O is d is 0, hence the torque is 0. So, that means you will not be able to rotate, whether you can able to rotate this gear wheel depends not only on the magnitude and direction of the force, but also on the where the line of action where you are applying the force. So, in the next lecture we shall review the Newton's law. So, thank you.